All right, let's dive in. Today we're going to trace the incredible journey of how we think about rivers. It's a story of how our understanding went from seeing them as just simple lines on a map to the incredibly complex living systems we know they are today.
So let's start with a question. It sounds kind of like something from a kid's book, right? How does a tiny mountain stream decide what to be when it grows up? But honestly, this simple question is what's driven decades of scientific discovery. I mean, how does a river system really work, from its humble start to its powerful end?
For the longest time, scientists were on this quest for a kind of universal blueprint, a single, clean, elegant theory that could explain the life story of pretty much any river anywhere on the planet. And then, bam, 1980 rolls around and it looked like they'd actually found it. A team led by Robin L. Vannote introduced this totally revolutionary idea called the River Continuum Concept. And their big idea was to stop thinking of a river as a bunch of separate pieces and instead see it as one single connected system that changes in a predictable way all the way from the mountains to the ocean. Okay, let's get into this, because the real beauty of this idea, the River Continuum Concept, or RCC for short, was just how simple and, elegant it was. It basically mapped out a river's entire life into 3 distinct, predictable stages. So first up, you've got the headwaters. Think small, chilly streams shaded by a thick forest canopy. Then, as those little streams start to merge, you get the mid-order rivers. These are wider, they're warmer, and they're way more open to the sun. And finally, all of those combine into these huge, deep, slow-moving rivers that meander their way toward the sea. It made sense, right? A totally logical progression.
Okay, but here's where it gets really cool. The model didn't just describe the physical journey, it connected it to the life inside the river. So up in the headwaters, the main energy source is fallen leaves from the forest. So what do you find? You find little insects called shredders that munch on those leaves. Then, in the sunny middle parts, algae starts to grow on the rocks, so you get grazers that scrape it off. And finally, in the big, murky rivers, tiny bits of food just drift down from upstream, feeding the collectors that filter it all out of the water. It's like a perfectly choreographed relay race, a perfect handoff.
The RCC was a brilliant map. It was groundbreaking, but as scientists started trying to use this map on rivers all over the world, they ran into a problem. What happens when the river goes completely off the map?
Yeah, it turns out nature doesn't always follow the rules. It's messy, it's unpredictable, and it rarely follows a simple straight line. The real world had all these twists and turns that the original blueprint just couldn't explain.
For starters, the RCC pretty much assumed a stable, steady flow. It had no real answer for these massive, game-changing events. We're talking catastrophic floods or years of drought that can literally just hit the reset button on the entire ecosystem overnight. And another thing, the model kind of pictured the river as this isolated channel, almost like it was a piece of plumbing. It completely missed the incredibly vital, life-giving connection between a river and the huge floodplains it spills out onto every single year. But maybe the biggest oversight, the real elephant in the room, was that the original blueprint imagined this pristine, untouched world. It had nothing to say about one of the most powerful forces shaping modern rivers: us, humans, and the massive concrete dams we've been building everywhere.
So you might think all these problems, these cracks in the model, would be a huge setback, right? But no, they didn't break river science, they blew it wide open. This kicked off a massive paradigm shift, a whole wave of new ideas designed to finally embrace all the complexity the RCC had missed.
All right, so first on the scene was the flood pulse concept. This idea totally flipped the script. It said, hey, that yearly flood, that's not a disaster, that's the heartbeat of the river. It's the main engine that drives the whole ecosystem, spreading nutrients far and wide and creating these critical nursery habitats for fish out on the floodplain.
So what about those dams we mentioned? Well, next came the serial discontinuity concept. This explained how dams act like these giant roadblocks. They create a sudden jarring break in that smooth, continuous flow of the river. It's like the river's story is flowing along, and then it just hits a wall.
And then scientists started thinking, what if we're only looking at the surface? So they started looking down. And what they found was this whole hidden world, the hypohoric zone. It's basically a secret third dimension of the river that flows through the gravel and sand underneath the riverbed, and it is absolutely critical for processing nutrients.
And all of this, all these new ideas, they all point to this massive shift in thinking. Scientists had to let go of the simple line. They started to see rivers as these complex systems that are defined by 4 Count them, 4 key dimensions. You've got the length, right, source to sea, the width, river to floodplain, the depth, surface to groundwater, and the 4th dimension, time itself.
Okay, so we've thrown a lot of concepts at you. Let's pull it all together and see what this new, much more accurate picture of a river actually looks like.
And this slide, right here, this sums up the whole journey perfectly. On one hand, you have the old blueprint, simple, straight, predictable, kinda lonely. But now, where science has taken us is to this modern view. It's multidimensional, it's messy, it's interconnected, it's dynamic, and, crucially, it acknowledges that we are a huge part of the story.
So if there's one number I want you to remember from all this, it's 4. Because this shift from a simple line to a complex 4-dimensional system isn't just some abstract thing for scientists to debate. Understanding all 4 of these dimensions is absolutely critical if we're going to tackle the real-world challenges our rivers are facing today. Because when you understand the whole system, you can make way smarter decisions. We're talking more effective conservation, smarter ways to manage our fisheries, better strategies for how we operate or maybe even remove dams, and protecting whole watersheds in a much more connected way. It allows us to work with the river, not against it.
So this whole journey from a simple line to this complex, living network really shows you something important about science, right? It never stands still. It's always growing, always evolving. And that leaves us, you and me, with the biggest question of all. Knowing everything we know now, what are the next questions we have to ask to protect these vital lifelines for the generations to come?